In this lesson, we're going to take a look at a few more examples of conservation of momentum in the form of collisions. So remember that the idea behind conservation of momentum is that our momentum at the beginning is still equal to the momentum at the end for a closed system not affected by outside forces. So we're really just going to practice more of what we've done already, but to add to that, we're going to take a look at a little bit more terminology, vocabulary, how do we classify collisions. So we've got two different main types of collisions. In the first type, objects bounce off each other after the collision. So they come together, they hit each other, they bounce off. For example, if you've ever played curling or billiards, the rocks or the balls, they hit each other and bounce off. A baseball hits a bat. Some car crashes, they might bounce off each other. And these kind of bouncy collisions, we're going to give it a fancy physics word, they are called elastic. Think of like a bouncy ball is elastic, it kind of compresses and then stretches again. Those are called elastic collisions. And contrasted with that, we have two objects sticking together after the collision. So instead of bouncing off each other, if a football player is tackling and holding onto the ball carrier, so he's grabbing, one person's grabbing another and they stick together, or a dart hitting a dartboard, they end up being one object at the end. Some car crashes, the cars stick together, or bullets entering and sticking inside a target, you get the idea. And when they stick together, these are called inelastic collisions. So elastic collisions bounce off. Inelastic collisions, objects stick together. Okay, so we're going to use that terminology to classify the collisions we're going to see in today's lesson. So let's keep going. Example number 1. A 1.5 times 10 to the, this should be times 10 to the 3, not times 103, sorry about that, times 10 to the 3 kilogram car traveling at 44 meters per second collides head-on with a 1 times 10 to the 3 kilogram car traveling at 22 meters per second in the opposite direction. So let's call our first car, let's call this car A. And let's, since they didn't give us east, west, north, south, we're going to call this first direction, this is going to be our positive direction. Collides head-on with car B, traveling at 22 meters per second in the opposite direction. So if car A was traveling in the positive direction, car B must be traveling in the negative direction. The cars stick together on impact. What is the velocity of the wreckage immediately after impact? So remember how we set this up? We start out with the momentum initial is equal to the momentum final. And we use this like fancy sigma thing to mean the sum, add them all together. And then we wrote this out as mass A, velocity A initial, plus mass B, velocity B initial. This is the sum of our initial momentums is equal to mass A, velocity A final, plus mass B, velocity B final. And we also said, well, if they stick together, if it's a collision where they stick together, then they're going to be going at the same velocity afterwards. So we're going to get rid of this VA and VB, and these are just VFs in general. We are looking for what is the velocity. So we're looking for this V final. In order to find that, we're going to factor it out on the right-hand side. So this is going to be V final times MA plus MB. They stick together, they're one big mass in parentheses. Left-hand side doesn't change, I'm just going to copy it down underneath. And the final step of our solving is going to be divide by this thing in parentheses, MA plus MB. Okay, let's see if we can use that to plug in our information. V final equals, again, watch out for the negatives and the positives. So our first mass is 1.5 times 10 to the 3. And my first velocity is a positive 44 meters per second, plus mass B, 1 times 10 to the 3. And our second velocity is a negative 22 meters per second. all over our two masses combined. So 1.5 times 10 to the 3 plus 1 times 10 to the 3. And that's what we're looking at. So we want to plug that into our calculator and see where that lands us. So I pull out my calculator and I'm going to type that all in. I might type in just the top first. It's going to be maybe a little bit easier. Plus 1 times 10 to the 3 times a negative 22. This is my numerator. Whoops. Exit. What did I do? Oops, I forgot the 3. There we go. Okay, and that's going to be all over my denominator of 1.5 E3 plus 1 E3 is 17.6 meters per second. Now, because they didn't give us directions north, south, east, west in our question, in order to give the direction of the final velocity, I'm going to think about it in terms of my original cars. So because this ends up being a plus 17.6 meters per second, I call plus the direction of car A. I'm going to call this 17.6 meters per second in the direction of car A. Because this ended up being a positive number, and we called positive the direction car A was going, and negative the direction car B was going. Now to finish this one off, there's a question, is it elastic or inelastic? Well, we know in our collision, we underlined in red, they stick together. Stick together is inelastic, so I'm just going to circle that down here. This is an inelastic collision. Okay, let's try a few more. Example number 2. An 18 kilogram curling stone is traveling due east at 2.6 meters per second. If you've never watched a curling game, go ahead and Google it to see what we're talking about. Curling stone. They throw a stone at other stones and try to get them to go to a certain place. Anyway, it strikes another curling stone, this one 12.5 kilograms, that is moving east at 1.2 meters per second. So it strikes, one stone strikes another stone that's already moving. After the collision, the first stone is moving east at 0.65 meters per second. What is the final velocity, magnitude, and direction of the second stone? So again, let's call our first stone, an 18 kilogram curling stone, let's call that stone A. Due east, so we know this is a positive 2.6. Strikes second stone, let's call this stone B, which is moving still east, so it's still going to be positive 1.2 meters per second. After the collision, the first stone is still moving east, so this is still a positive 0.65, and it's the first stone, so we're talking stone A. And we want to know what is the final velocity, magnitude, and direction of second stone B. All right, so let's start out with this MA VAI plus MB VBI is equal to MA VAF plus MB VBF. Now in this case, we don't know that their final velocities are going to be the same. If they were, that would indicate that they'd stuck together, but we're trying to find the final velocity of stone B. That's this guy right here. This is what we're aiming in for, final velocity of stone B. So I'm going to subtract my MAVAF to the other side and then divide out my MB. So that's going to end me up with VBF is equal to MAVAI plus MB VBI, subtract MAVAF all over mass B. Now let's see if we can start to plug in some numbers. I've got VBF is equal to MA was 18, VAI 2.6, plus MB 12.5, or VBI 1.2, and then minus MA again, 18, and VAF is a positive 0.65. All of that divided by the mass of B, the 12.5. Let's see if we can work that on a calculator. So let's see if we can manage to type this into the calculator. I'm going to go 18 times 2.6 plus 12.5 times 1.2 minus 18 times 0.65, whoops, times 0.65, and all of that divided by 12.5 gives me a final velocity of 4.008. If I round that to 2 or 3 sig figs, I'm looking at 4.0 or 4.01 meters per second. And in this case, I do have a reference for a positive direction because I was talking east. Everything was going east, so positive is still going to be east as my direction. Now, is it elastic or inelastic? For that, I need to look at the final velocities of both objects. So first stone is moving at the end at 0.65 meters per second east. Other stone is moving at a different velocity. Since the velocities are not the same, I'm looking at an elastic. They bounced. Elastic collision. In order for it to be inelastic, they have to have the same final velocity. So we got one more example to go before you start the homework, example number 3. And in this case, I might encourage you to pause your video, try this one for yourself, and then come back and see how you did. So, a 550 gram can of soda is thrown due east at 25 meters per second. Let's call this object A, can of soda. Now look out, this is in grams, I'm going to need to convert that. Due east, so east positive 25 meters per second. A 12 gram bullet, let's call this B for bullet, that's kind of handy, and again grams, watch out, traveling west at 250 meters per second, strikes the can, passing through it. So west is going to indicate we have the negative velocity. Afterwards, the bullet continues west, bullet B continues west at 55, so west is a negative 55 meters per second. What is the final velocity of the can? Velocity A, final, magnitude and direction. So first thing I'm going to need to do is take mass A, which is 550 grams, and convert that into kilograms. So I'm going from grams to kilograms. 1 kilogram is 10 to the 3 grams. Multiply across the top, divide by 10 to the 3, and that gives me 0.55 kilograms. Same thing with mass B, but this time I'm starting with 12 grams. Divide by 10 to the 3 grams per 1 kilo. It gets me 0.012 kilograms. All right, let's see if we can set this up. MA VAI plus MB VBI is equal to MA VAF plus MB VBF. We got this memorized already? I hope so. We've used it a lot. Here we go. What are we looking for? What is the final velocity of the can after the bullet goes through it? So in this case, we're looking for velocity A final. That's what we're aiming for. So again, the rearranging, subtract the MB VBF to the other side and divide by MA. So this is going to be VAF equals MA VAI plus MB VBI minus MB VBF all over MA. Let's plug in some numbers. VAF equals mass A 0.55 kilograms, VAI positive 25 meters per second, MB 0.012, and VBI is a negative 250 meters per second. Subtract from that mass of the bullet again, 0.012, and VBF is at a negative 55 meters per second. All of that divided by 0.55. So again, as you type this in, watch out for your positives and negatives. Here we go. 0.55 times 25 plus 0.012 times negative 250 minus 0.012 times negative 55. Take that number, divide by 0.55, And that gets me a final velocity of 20.7, well, that would be 3 sig figs meters per second. Okie dokie, so we've got 20.7 meters per second. In this case, positive does have a reference frame. It is east. So there we have our velocity. Elastic or inelastic? Well, the velocity of the bullet is not the same as the velocity of the can, so the bullet did not stick in the can, so we are looking at an elastic collision. All right, that's it for its examples. Now it's your turn.